We're now going to talk about the definition, the concept of current density. And as you can see here, this is an area density, so our understanding of the concept and the definition are really one and the same. So this current per unit area, I divided by A, is what you definitely want to memorize. Then our units fall right into place. I has units of amps. Area has units of meters squared. So the current density is the amps per meter squared flowing through the wire. Now, we don't want to memorize more than we have to, so we are going to use our already memorized that I equals Q nav in our equation for J is I on A. We can see we lose the A. So we actually get an equation for the current density, the amps per meter squared, based on the charge on the electron, the number density of electron carriers, and the velocity of each of those charge carriers or the electrons. And we have down here just the reminder that V is the drift velocity, N is the number density of charge carriers. Technically, it's the electrons. For us, it'll be the conventional charge, really same thing numerically. So it's the number per area. So that's where we get our meter squared comes back into play. Remember, this is the number density is the number per meter squared. And later in the course, when we introduce magnetism, we'll see how that can actually be measured. That's kind of a cool experiment we'll talk about later on. And the final thing on this page of notes, again, a relatively short page of notes, is to understand the relationship between the current density and the current. Now, we will see later in this chapter, so I'm not going to really talk about the proof of that. We'll see why it is so, that the current density is a vector quantity and always follows the electric field. So J always goes with E. Please make sure you get that into your notes. Now, here what I'm showing is kind of just a generic electric field impinging on a wire. So we just have it coming in at some random angle. And if we're interested, as we are when we're talking about current, the flow of charge along the wire, then what we want to see is how much of those positive charge carriers that under normal circumstances, right, just move with the electric field, will actually be pulled perpendicularly through the cross-sectional area along the wire, which would be our electric current. Well, to do that, we need a cosine. So we need J cosine theta gives us the portion of the J vector flowing in the direction of the N hat vector. So this is why current is a scalar quantity, even though we think of it as a vector quantity, because we end up thinking of it as more in terms of the J vector than just the current. But the current is a scalar, and we need to know that for our multiple choice type questions for understanding the concepts. Current is a scalar. Current density is a vector quantity. Since current density is current per area, the area here takes care of our units. So everything, of course, works out nicely mathematically, but it's J dot A. So I equals J dot A, and of course, we have the calculus version of integral J dot dA that we'll see the distinction of when to use the regular non-calculus version, J dot A, and when to use the integral on our next example in our notes. So again, I'm zooming out here. Make sure you get all of the annotations. And we will, of course, discuss this more when we firmly link the J vector and the E vector together in a couple pages of notes.